Hi, and welcome to OntologyTalk. I'm Adam Pease, and we have a special guest today, Chad Brown. Dr. Chad Brown is an expert in higher order logic. He's a mathematician, a computer scientist, and a logician. He's been working primarily on higher order logic in his work on automated theorem proving. And he's also the creator of the Satilax higher order prover that for a number of years was the winner of the yearly CASC automated reasoning competition. So welcome, Chad.
Thanks for having me on, Adam.
Yeah, it's really a pleasure. So maybe we could start just with a very general question for our listeners who might not be intimately familiar with automated theorem proving and its various sorts of divisions and areas. What is higher order logic?
Okay, well, often higher order logic would be presented as an extension of first order logic. That's slightly ahistorical, because it really goes back to the work of the German mathematician Frege in the late 19th century. And Frege really developed the first, what I would call formal logic, a language for writing down propositions and precisely saying which of those are provable. And Frege's language was, I think it's fair to say, higher order. And of course, a lot happened after Frege. But the important thing in, let's say, in Frege's language that made it higher order, is you could do something like quantify over predicates. In particular, if you quantify over binary relations, you can directly define the transitive closure of the relation. The least relation is transitive and a super relation of the one you're given. And you can't do this in first order. So unfortunately, Frege's logic turned out to be inconsistent. This was the Russell paradox. And so Russell created a type theory that was very similar to what Frege was doing, but basically introduced types in a way that gets around the paradox. And this was what was used in Russell and Whitehead's work, really famous work, Principia Mathematica. Russell's type theory was a bit complicated, needlessly so, and this was recognized by people in the next few decades, and you ended up with what they called simple type theory. So in fact, simple type theory is simple because it's a simplification of Russell's type theory. And simple type theory is what people often associate with higher order logic now. So in particular, the formulation given by Alonzo Church in 1940, using simply type limited calculus. And nowadays, if people say higher order logic, it's generally some extension of Church's type theory. Church's type theory certainly qualifies as higher order logic, but often it's used more generally for things that include Church's simple type theory. And the important thing there is, once again, that you can quantify over predicates. First order case, you can't quantify over predicates. So you could say first order logic is a higher order logic where you are disallowed from quantifying over predicates. And one reason first order logic is very popular among, let's say, mathematicians, logicians, is because you have very nice theoretical results. You have Tarski's semantics, and you have soundness completeness theorem, things like compactness and Lovener-Skolem. But in the case of Church's type theory, the higher order case, you also have a semantics by Leon Hinken where you get the same results. So higher order logic in the sense of Church's simple type theory really does have very similar properties to first order in that sense. So that's roughly what it is, without giving a grammar and saying what the terms are.
Well, fascinating, because in fact, I always think of higher order logic as being something beyond first order that would have come after first order, but you're saying it actually goes back to Frege, that Frege's original formulation of logic was already a higher order logic. He just didn't quite work out some of the details, and so we had to rely on Russell and Church to kind of fix these things and give us higher order logic as a distinct advance beyond what most students now are introduced to in a basic logic class, which is first order logic.
Yes. So I'd say the first order formulations largely go back to Hilbert and the people who worked with Hilbert. Right. This is obviously after Frege. So if people disbelieve me about Frege, which I would encourage people to disbelieve me, go back and look for his definition of transitive closure, and You would have to convince yourself that this is not higher order. It very clearly is.
And also interesting that just to make clear to people what, from a usage standpoint, is the difference with higher order. You've given us sort of the evolution, the history of the people involved. You talked about quantifying over predicates. So can you give us an example, as kind of a real world example of quantifying over a predicate that wouldn't be allowed in first order, but that now you could take advantage of if you have a higher order language?
Yeah, I'd say there's two different kinds of examples. One is making definitions, and the other one is stating properties. Right? So I already mentioned transitive closure as an example of a definition. Other definitions you can make finiteness, whether or not a property is finite. That requires quantifying over properties. And actually an interesting one that you'll find in Church's 1940 paper is you can define equality, right? This is usually called the Leibniz notion of equality. That two things are equal if they share all the same properties. Now, how do you say they share all the same properties? You can't quantify over properties, right? So technically you would say A equals B if for all properties Q, if QA holds, then QB holds. You might expect equivalence, but implication is actually enough. Okay, so those are definitions. In terms of properties, probably the most familiar one to people is the induction axiom for the natural numbers, right? Where you say property P holds for all natural numbers whenever it holds for, let's say, 0. Equally well start at 1, but let's start at 0. If it holds for 0, and whenever it holds for n, it also holds for n plus 1. Or you usually say the successor of n. So base case, successor case. And to state that, you really need to say for all properties P. That you can directly do in higher order. And if you wanted to do it in first order, you'd have to have some first order notion of property. And there are also other examples people might be familiar with, like in set theory, to state that for every set X and every property P, there's a set Y that contains precisely the elements of X that satisfy P. You can't do this unless you have some way of talking about P. Now, people listening may object that obviously you have first order piano arithmetic. So how do they do this? Well, they don't have a single induction axiom. They have an induction scheme. So it takes infinitely many axioms. And this is typically the case in set theory as well, that there are first order set theories, but they have infinitely many axioms because you introduce these schemes. And this is very similar, but there is an important technical difference. If you take the induction axiom of the natural numbers, first order piano induction really says induction holds for all first order definable properties. Whereas in the higher order case, it says for all properties, in particular the ones you can define using higher order logic. And as I showed with or mentioned with the transitive closure example, there are more properties you can define with higher logic than you can with first order logic. So it's actually technically stronger to have the higher order axiom. It's a single axiom now, and it's a stronger axiom.
Okay, and maybe I could also just draw a parallel with some content that our viewers from my other videos might be familiar with, because you mentioned transitive closure. That's a really important one in ontology. For example, that a wheel is a part of the chassis of a car, which is a part of the car entirely. And so we want to be able to talk about transitive relations, and physical parthood would be a transitive relation. So as we don't have to, if we're in higher order, state the axiom of transitivity again and again and again ad nauseum for every single transitive relation we might have in our knowledge base.
Yes.
So that's a really valuable and time and space saving thing to be able to do.
Yes, these are two slightly different things, but it's an important example. So you were saying in higher order, you could say something like, for all relations, if R is transitive, which is already something, how would you say this in first order? You can't have a predicate over a relation. Then the usual notion of transitivity follows. But let's say you had a relation that's not transitive. Can you think of an example of a relation that's not transitive?
It's not transitive. On top of.
Okay. And you could imagine, oh, yes, that's good. You could also say parent, right?
Parent, yeah, because we have parents and grandparents and great-grandparents, and so parent is not transitive. You're right, the parent of the child is not the parent of the grandchild. It's
Yeah,
the grandparent.
exactly. I actually thought of that
Yeah.
because you said on top of, and you can picture the family tree.
Yeah.
So a very similar example. And you might want to consider the transitive closure of this, which is obviously ancestor, right? Or on top of, maybe it's vertically higher in some way.
Yeah.
In higher order, you can directly define the transitive closure of the relation and talk about it. You don't have to have a separate relation that you explicitly define and then write down the properties. And even if you did write down the properties, how you could say it's transitive if you gave it a new name, let's say ancestor. You could write down, yes, if it's parent, then it's ancestor. You could write down that it's transitive. But how do you know it's not the least one? How do you know it is the least one, right? There might be, let's say, spurious examples of ancestor that you haven't ruled out, and you have no way to rule them out in first order.
We'll pause here and return in a moment for part 2 of my interview with Dr. Chad Brown.